All right, good morning. So let's get started. So last time we actually looked at how we can characterize corner points in a general LP problem. So essentially, we know what corner points look like when we have LP problems with only two variables. So whenever two lines intersect, that becomes a corner point. But then we said that whenever we have more than two variables, then it's not easy to draw the feasible region. So we need a sort of alternate characterization of corner points. And essentially last time we did that. So basically we had the correspondence between corner points and basic solutions which are feasible. So each corner point corresponds to a basic feasible solution, and conversely each basic feasible solution actually corresponds to a corner point. And before, in this class actually, we had mentioned the importance of corner points. In particular, if there's an optimal solution, then there's a corner point which is optimal. So now that we know what corner points look like, we can actually sort of come up with an algorithm. Okay, so we can try to sort of write down all possible corner points, and then we can see which one gives us the best solution. So essentially, I'm going to start with a so-called simple-minded algorithm. So let's assume that we have an LP problem, given an LP problem in standard form. So we know that every LP problem can be converted into standard form, so we have seen this before. So we can first of all compute all basic feasible solutions. I'll just write BFS for short. And then we can pick the one with the best objective function value. Now, what's the idea behind this sort of simple-minded algorithm? Well, we know that if there's an optimal solution, then there's a corner point which is optimal. We also know that each corner point corresponds to a basic feasible solution, or BFS for short. So essentially what I can do is I can try to compute all basic feasible solutions of a given problem. Then I'm going to evaluate the objective function. I'm going to compute the value of the objective function at each basic feasible solution. And whichever gives me the best objective function value, I'm going to sort of declare it as the optimal solution. Okay? So it's a very simple algorithm. However, there are some problems with this algorithm, and I'm going to try to argue what those problems are. So what are the problems with this algorithm? All right, so can anyone think of any problems with this algorithm? So if you try to implement this algorithm, then what kind of difficulties can you face? There can be a lot of basic feasible solutions. I'm going to actually illustrate that that can be true. So the first problem is that, so there may be too many basic feasible solutions. So now let's try to sort of get an idea of how many basic feasible solutions we can have. So if there are M constraints, M equality constraints, and N decision variables. So remember, we always assume that number of decision variables is at least as large as the number of equality constraints. Then how many basic feasible solutions can I have? So what's the largest number of possible basic feasible solutions for such a problem? Well, first of all, to answer that question, we need to sort of figure out what the basic feasible solution is. So remember, we have M constraints, right? So we have M equations, basically. And we have N unknowns, or N decision variables. So what we do is we actually pick M of them, right? So from among these N decision variables, we pick M of them, where M is the number of equations. And then we sort of set the rest of the unknowns to 0, and we only solve for this subset of variables, basically, right? So as a result, for each basic feasible solution, there is a set of corresponding basic variables, right? And by changing that set of basic variables, I can actually obtain potential different basic feasible solutions. Is that clear? Okay, so then, what's the largest possible number of basic feasible solutions? So, number of basic feasible solutions cannot be more than what? So what's the largest number that I can have? Well, so from among n decision variables, I'm going to pick m of them, right? And I can do it in this many different ways. Okay? So I can choose m variables, m basic variables from out of n decision variables in that many different ways. Okay? So why do I have inequality over there? Why not equality? So why do we have less than or equal to? So first of all, some basic solutions can be infeasible. That's good. Anything else? So for example, if you recall the last example that we did, n was equal to 4 and m was equal to 2 in that example, right? So 4 choose 2 is equal to 6. Okay? So it says that number of basic feasible solutions cannot be more than 6, but in that example we had actually 5 basic solutions only. Okay? So where does the inequality come from? So
Our region does not contain the solutions.
what do you mean? So the first reason why we have inequality is the following. So not every basic solution will be feasible, right? Okay, so there may be some basic solutions which are not necessarily feasible. So that's the first source of that inequality. What else can we have? Well, we assume that we don't have any redundant constraints because we can eliminate them. Okay? So if you recall the last example that we had, not every choice of m variables will necessarily give you a basic solution, right? So if you look at the last example that we had, for a certain choice of basic variables, the corresponding B matrix was not invertible, basically, right? Okay? So that's the other source of inequality, basically. So as a result, two things may happen. First of all, not every basic solution is feasible. Okay? Or not every basic solution is necessarily feasible, I should say. Okay? That's the first problem. And secondly, not every choice of m decision variables will give you a basic solution. Okay? So as a result, the largest you can have is n choose m. Is that clear? So that is an upper bound on the number of basic feasible solutions we can have. All right, so let's look at an example. For example, if I have 20 decision variables and 10 equality constraints, then I'm going to sort of give you what this number is for these values of n and m. So if I have 20 variables, then number of ways that I can pick 10 variables out of 20 is given by any estimates on this number. So how large can this number be? So this number is equal to 184,756. Okay, so which means that in the worst case, you can have as many as this number of basic feasible solutions. Okay? And if you want to compute each one of them, well, that's going to take some time, basically, right? So, I mean, you can still do that. There's still a finite number of them. But that finite number is not a small number, basically, okay? So, as a result, even for 20 decision variables and 10 equations, the number of basic feasible solutions can be almost equal to 200,000 almost, okay? And the problem is that, so right now, such an LP problem, so an LP problem with 20 decision variables and 10 equations is a very small LP problem for now, okay? So such an LP problem is actually considered tiny. So which means that if you actually sort of have such an LP problem, and if you give it to the Excel solver, then it's going to give you solutions within the fraction of a second, basically, okay? So as a result, we need something smarter than that. So if you want to write down all possible basic feasible solutions, then this may take some time, okay? And remember, so there were some examples such as the cutting stack problem where number of decision variables can be quite large, basically, right? Okay? And just to give you an idea, So right now, the largest LP problem that can be solved has about 25 million variables and 12 million constraints. Okay? And I don't want to even sort of compute that number. Okay? So as a result, you need to do something smarter than this. So this is the first problem. Okay? So if you want to write down all possible basic feasible solutions, there may be too many of them, and that's going to take some time. What is the other problem? So this implies that computing all basic feasible solutions is not a good idea. Any other problems? Now remember, so when we discussed LP problems, when we classified them, we said that an LP problem may have an optimal solution, right? It may be infeasible, or it may be unbounded, basically, right? So if the problem is infeasible, then actually this procedure will tell me whether there is a basic solution or not, okay? So if I try all possibilities and if none of them is feasible, then there's no basic feasible solution, which implies that there's no feasible solution. So I can actually, by using this sort of simple procedure, I can tell you whether a given LP problem is infeasible or not, okay? If I try all possibilities and if none of them actually gives me a basic feasible solution, then my problem cannot have a feasible solution. Why not? Because earlier we showed that, you know, if there's a feasible solution, then there's a corner point for LP problems in standard form. Okay? Well, there's this other option. So what if the problem is unbounded, right? So how will this algorithm tell me if the problem is unbounded? Because all this algorithm does is basically it looks at all possible corner points and it looks at the objective function and it picks the best one. Okay? But that solution may not necessarily be an optimal solution, basically, right? If the problem is unbounded, then there's no optimal solution. Okay? So the second problem is basically, so what about unbounded problems? So right now, I mean, the way I wrote it, this algorithm has no way of knowing whether a given problem is unbounded or not. Okay? It cannot tell you actually whether the problem is unbounded. Does everybody see that? So is that clear? Okay. So, well, what are we going to do? Well, the simplex method, which we're going to start discussing today, so the simplex method computes vertices or computes basic feasible solutions in a clever and systematic way. Okay? And I'm going to try to explain what I mean by this in a minute. So rather than computing all possible basic feasible solutions, it actually does this in a systematic way. Okay? And since it does it in a systematic way, in most cases, it does not have to sort of compute all possible basic feasible solutions. Okay? So I'm going to give you examples, as I said. So essentially, the idea is pretty simple. So given a basic feasible solution, it only considers so-called neighboring or adjacent basic feasible solutions. So we gave an example of this earlier. So essentially, in 2 dimensions, we know that there's a correspondence between corner points and basic feasible solutions. So in this example, for example, there's 4 corner points, which I'm going to call 1, 2, 3, and 4. So what do we mean by adjacent basic feasible solutions? So for example, 1 and 2 are adjacent because I can move from 1 to 2 using the edge of the feasible region. Okay? But 1 and 3 are not adjacent because I cannot move from 1 to 3 by using a single edge of the feasible region. Okay? So essentially, if I'm looking at basic feasible solution 1, then the simplex method only considers 2 and 4 as possible alternatives. Okay? It does not look at 3 directly. We're going to see why this is the case later on. But by doing that, it turns out that you get a much better algorithm than this one. Okay? So you have an algorithm that gives you an optimal solution without looking at all possible basic feasible solutions. Okay? So let me give you a formal definition. So 2 basic feasible solutions are adjacent if they have m minus 1 basic variables in common. Where m is the number of equality constraints. So what do I mean by this? So we know that for a basic variable, if I have m equations, then I need m basic variables, okay? And for every choice of m basic variables, there may be a corresponding basic solution, right? There may or may not be, depending on whether the matrix P is invertible or not. And I'm going to call two basic feasible solutions adjacent if they share m minus 1 basic variables in common, okay? So only one basic variable is different. So just to give you an idea, for example, in one solution, I can have my basic variables are x1 and x2. My non-basic variables are, x3 and x4. In another solution, I may have x1 and x3 as basic solutions, and x2 and x4 as non-basic solutions. So would these two be adjacent basic feasible solutions? Assuming that they're feasible. The answer is yes, because m is equal to 2 in this case, okay? So m minus 1 will be equal to 1, and I'm going to call two basic feasible solutions adjacent if they have one basic variable in common, okay? And in this case, x1 is the common basic variable, so as a result, these two would be adjacent basic feasible solutions, okay? If I want to give you another example, so if my basic variables are, let's say, x3 and x4, and non-basic variables are x1 and x2, so would these two be adjacent basic feasible solutions? No, because they have no basic variables in common, basically, right? Okay, so as a result, these two, the first one and the third one, would not be adjacent basic feasible solutions. So it's a very simple definition. So whenever I have two basic feasible solutions, I look at their sort of corresponding basic variables. And if m minus 1 basic variables are the same, okay, so which means that if both basic feasible solutions have m minus 1 variables in common, then I'm going to call them adjacent, okay? So as I said, it's a very simple definition, and adjacent actually corresponds to, in this picture, 1 and 2 are adjacent, but 1 and 3 are not adjacent, basically, okay? Indeed, if you look at the previous example, you're going to see that for every pair of adjacent basic feasible solutions, there's exactly one basic variable in common, okay, in that example. Okay? Is that clear? So, all right. Now, there's one other issue that we need to talk about before we start the algorithm, and it's called degeneracy. And I'm going to try to explain what I mean by this on an example. So suppose that we have the following system. So once again, I mean, corner points are only determined by the feasible region, so I just give you the feasible region, so there's no objective function. Now let's quickly draw the feasible region in this example. So this is the first constraint, and this is the second constraint. And then what does the third constraint look like? If x2 is 0, x1 is equal to 9, so which is somewhere over here. And if x1 is 0, x2 is equal to 4.5, which is the midpoint here. So it goes through these 2 points, but at the same time, it actually goes through the intersection point as well. Okay? And then we have non-negativity, so you can easily verify that this is a feasible region. Now, we have seen a similar example before. I think it may be even the same example. The problem is that, so if you look at this corner point, actually there are 3 lines intersecting at the same point, right? So, and that point is given by 3, 3, I think. Okay? So all 3 lines actually go through the same points. And let's see what kind of implications that has, okay, in terms of our basic feasible solutions. So just like we did earlier, the first step is to convert it into standard form. So is this feasible region in standard form? No, it's not. So we need to fix certain things. So what do we need to fix? So the first three constraints should be equality constraints, basically. So how am I going to do that? So I'm going to add select variable for each constraint. So the first one will be x1 plus x2, and I'm going to call x3. Now I'm going to have equality equals 6. Then I'm going to call x4, the second select variable, which is equal to 3. And then x1 plus 2x2, I'm going to call x5. And the right-hand side is equal to 9. And each of my variables is non-negative. So the last row is just a shorthand for saying that each variable is non-negative, okay? All right, so let me just write down my A matrix. My A matrix will be given by 1, 1, 1, 0, 0, 1, 0, 1, 0, 0, 1, 0, 1, 0, 1, 2, 0, 0, 1. So essentially, this is my matrix of coefficients in the system. Okay. And what's my right-hand side vector B? So it's going to be given by 6, 3, and 9. Okay. So just like we did in the last example, I'm going to try to compute basic feasible solutions for the standard form, basically. Okay. So so how many basic variables do I need for such a system? 3, because there are 3 equations, basically, right? So as a result, I need 3 equations. So first, I'm going to start with the following. So I can set xb to be the first 3 variables. In that case, xm will be equal to the 4th and the 5th variables. Okay. So what's the corresponding B matrix? So it's going to be the first 3 columns of A, basically, right? Corresponding to x1, x2, and x3. So I'm going to have 1, 0, 1, 1, 1, 2, and 1, 0, 0. What is my N matrix? So the last 2 columns of A, basically. I'm going to have 0, 1, 0, and 0, 0, 1. So I'm going to set all of my basic variables to non-basic variables to 0. Okay, and then I'm going to solve for my basic variables, which are given by x1, x2, and x3. So this is given by, remember, B inverse times little b. Okay, I'm solving for basic variables. And if you solve for this system, if you invert b and multiply by little b, you get 3, 3, 0. Okay, so the corresponding solution is x1 is equal to 3, x2 is equal to 3, x3 is equal to 0, x4 is equal to 0, and x5 is equal to 0. Would this be a feasible solution? So basically, all the variables are non-negative, so as a result, it's a feasible solution for this problem, right? Okay. Now, what is the corresponding solution in this picture? So it's exactly the intersection of this point, so which is given by 3, 3, right? So if I look at x1, x2 components, they're given by 3, 3, so I actually get precisely this point right here, okay? Now, there's one thing that I'd like you to sort of draw your attention to. So if you look at the basic variable x3, okay, x3 is a basic variable, but its value is equal to 0, basically, right? Okay? Now, in all the examples that we have seen so far, all the basic variables always had positive values, basically. Okay, so this is the first example where out of 3 variables, only the first 2 have positive values, but the third one is equal to 0. Okay, so in a sense, the third basic variable is like a non-basic variable in some sense. Okay, so all non-basic variables are equal to 0, and the third basic variable is also equal to 0. Okay, so let me circle that. So x3 is a basic variable, but its value is equal to 0. Does everybody see that? So let me give you a definition. So in a basic feasible solution, the matrix B is called the basis matrix, or just the basis. For example, in the solution, my matrix B, which is given by 1, 1, 1, 0, 1, 0, 1, 2, 0, would be the basis matrix corresponding to this basic feasible solution. So this is just a definition. So from now on, whenever I talk about basis, I mean the matrix B, basically, okay? Here's another definition. A basic feasible solution is called degenerate if there is at least one basic variable whose value is equal to 0. So if I compute a basic feasible solution, and if there's at least one basic variable whose value is equal to 0, then I'm going to call that basic feasible solution a degenerate basic feasible solution, okay? So now if I go back to this example, would this be a degenerate basic feasible solution? Yes, because x3 is a basic variable and its value is equal to 0, okay? On the other hand, if all the basic variables are positive, then we call it, then it is a non-degenerate basic feasible solution. So if you go back to your previous example in your lecture notes, basically all the basic feasible solutions in that example were non-degenerate, okay? Because all basic variables had strictly positive values. However, in this example, x3 is a basic variable and its value is equal to 0, so as a result, we have a degenerate basic feasible solution, okay? Is the definition clear? So it's a simple definition, okay? All right, so you may say, well, so what? Well, I'm going to give you what the problem is in such a case. All right, so now what I'm going to do is, I'm going to change my basic variables, okay? So instead of having x1, x2, and x3, I'm going to look at a different set of basic variables. And I'm going to pick, let's see, so x1, x2, and x4. And my non-basic variables then will be x3 and x5. Now, what's my basis matrix in this case? So my basic variables are x1, x2, and x4. So I'm going to pick the first, second, and the fourth columns of A, right? Okay. So let's do that. I have 1, 0, 1, 1, 1, 2, and then 0, 1, 0. What is my AND matrix? The third and the fifth columns, so which are 1, 0, 0, and 0, 0, 1. So once again, I'm going to set all my non-basic variables to 0. And I'm going to solve for my basic variables, which are x1, x2, and x4. So it's given by b inverse times little b. And if you take the inverse of b and multiply by little b, you get 330 again. Okay? Now let me write down the corresponding solution. So x1 is equal to 3, x2 is equal to 3, x3 is equal to 0, x4 is equal to 0, and x5 is equal to 0. Now let's just compare this result with the previous one. So do you see any difference between the two? Well, we get the exact same solution basically, right? Okay? Now, despite the fact that we're using a different set of basic variables, we get exactly the same solution. Okay? There's one difference though. So, in this solution, x3 was basic and its value was equal to 0. In this solution, x4 is basic and now its value is equal to 0. Okay? So therefore, the only change between these two is that, x1 and x2 are the same basic variables in both solutions. So here x4 is basic but has a value of 0. Here x4 is non-basic and has a value of 0. Over here x3 is basic and has a value of 0. Here x3 is non-basic and has a value of 0. So essentially, the only difference between these two solutions is that the label of x3 and x4 only change. Okay? So one of them was a basic variable and the other was non-basic and vice versa. Okay? But all the values are the same. And if I go back to my original problem again, so what does this solution correspond to in this picture? Well, the same solution again. Okay? Now, hopefully you start to see what's going on. So in the previous example, whenever we change the set of basic variables, we always had a different corner point, basically. Okay? However, in this example, I changed my basic variables and I'm still looking at the same corner point, so nothing changes. Okay? And the reason, as I'm going to explain in a minute, is that so at that corner point, there are actually 3 lines intersecting at the same point. Okay? And that will cause us some problems later on. I'm going to give you one more example. So note that this is also a degenerate basic feasible solution. And lastly, I'm going to actually look at x1, x2, and x5 as my basic variables. Then my non-basic variables will be x3 and x4. Now, what's my B matrix in this case? So I'm going to look at the first, second, and the fifth columns of A, right? So let's do that. I have 1, 0, 1, 1, 1, 2, and 0, 0, 1. And what's my N matrix? I'm going to look at the third and the fourth columns of A, right? So 1, 0, 0, 0, 1, 0. Okay, so now I'm going to set all my non-basic variables to 0. And my basic variables, which are x1, x2, and x5, will be given by b inverse times little b. And again, if you do this sort of on your calculators or on your computer, you're going to see that the answer is, again, 330. What's the corresponding solution? Well, again, x1 is equal to 3, x2 is equal to 3, x3 is equal to 0, x4 and x5 are also equal to 0. Well, so is it a different solution? No, it's still the same solution, basically, right? Now, what's the difference? Well, in this case, x5 is a basic variable, okay? But its value is also equal to 0. So essentially, in going from this one to this one, then the label of x5 was basic here, non-basic here, so it becomes basic here. And here, for example, x4 was a basic variable, and its value was 0. Here, x4 is a non-basic variable, and its value is equal to 0. Okay. So in these examples, in these 3 examples, I change my basic variables every time, and all of them actually give me the same solution. Okay? Now let me try to illustrate why that's the case. So remember, in 2 dimensions, every corner point is given by the intersection of 2 lines, basically, right? Okay? So last time we had this example. But if you look at a point such as this one, okay, there are 3 lines intersecting at the same point. Okay? And we know that every pair of intersections actually gives us a basic feasible solution. Okay? So as a result, from these 3 lines, I can actually pick any 2 of them, okay? And I can express this corner point as the intersection of those 2 lines. Okay? And if you think about it, so from these 3 lines, I can actually pick 2 lines in 3 different ways. Right? And that's exactly 1, 2, and 3, basically. Okay? So as a result, by looking at those 3 lines, whenever I pick 2, that actually corresponds to picking a certain set of basic variables. Okay? When I look at a different pair of lines, that corresponds to a different basic feasible solution. And finally, when I look at the final pair, then I get a different basic feasible solution. Okay? So since 3 lines intersect at the same point, that point can be expressed as the intersection of 2 lines in 3 different ways. So as a result of which, these 3 basic feasible solutions actually correspond to the same corner point. Okay? So unlike the previous example then, in that example, all basic feasible solutions correspond to a different corner point. So if you have degeneracy, then different choice of basic variables may give you the same corner point. Okay? And this example illustrates that, basically. Does everybody see that? Okay. Now, why is this important? Well, this is going to be important later on when we talk about the simplex method, because the simplex method actually works with basic variables. Okay? And later on, we're going to see that, for example, if you look at our definition, so these two are adjacent basic feasible solutions, essentially, right? Why is that? Because here, m is equal to 3, and two basic variables are in common, basically. Okay? So they're adjacent basic feasible solutions, but they are so adjacent that they're the same in some sense. Okay? So that's the problem. Okay? Any questions so far? All right. Let me write down my remarks. So in this example, 3 different choices of basic variables all lead to the same corner point. So note that, as I said, this corner point can be expressed as the intersection of 2 lines in 3 choose 2, which is equal to 3 different ways. So essentially, that 3 and this 3 is not a coincidence, okay? It's the same 3, basically, okay? So since I can express that point as the intersection of 2 lines in 3 different ways, that means that I can find 3 different sets of basic variables which still represent the same corner point, okay? So what's the bottom line then? Well, the bottom line is the following. So in a degenerate basic feasible solution, more than one basis can represent the same corner point. And that's exactly what's going on in this example. So we have 3 different choices of basic variables, but they still all represent the same basic feasible solution, okay? So later on, we're going to see that degeneracy needs to be handled in a special way. In simplex methods. So we're going to see that later on. Okay? I mean, at this point, you only need to remember that whenever you have degeneracy, despite the fact that you change your basic variables, you're still looking at the same solution. Okay, so that's important to sort of remember. So as a result, I'm changing my basic variables, but the values are still the same. So I'm still looking at the same corner point in the 2-dimensional picture. Okay, and this has not happened in the previous example, because in the previous example, there were no degenerate basic feasible solutions. So every time we changed basic variables, we moved to a different corner point. Okay? Any questions? All right. So now we're going to start discussing the simplex method. So this is my first example. So let's consider the following problem. I'm trying to maximize minus 3x1 plus 2x2 And my constraints are given by minus 3x1 plus 3x2 is less than or equal to 6. Then minus 4x1 plus 2x2 is less than or equal to 2. Then x1 and x2 are non-negative. Well, this LP problem has only two variables, okay? And as a result, we know how to solve this problem already, right? So you may say, well, what's the point of trying to illustrate the method on this example? We already know how to solve this problem. Well, I'm going to try to see how the method works on this example because we can see what's going on, okay? So we're going to sort of try to get an idea of how the simplex method works. So first, as usual, I'm going to start by drawing the feasible region. So what does the first constraint look like? What's the region defined by the first constraint? Well, if x1 is 0, x2 is equal to 2, right? So somewhere is here, it's 2. And if x2 is 0, x1 is equal to minus 2, right? So it's going to go through these 2 points. Okay. Now, which is the correct side? Right or left? So if you plug in 0, 0, it's satisfied. So as a result, the origin is on the right side. So this is the first constraint. What does the second constraint look like? If x1 is 0, x2 is equal to 1. So it goes through this point right here. And if x2 is 0, x1 is equal to minus 1 over 2, basically, right? Okay? So it's this point right here, minus 1 over 2. It actually goes through these 2 points. So this is what the second constraint looked like. Again, which is the correct side? So again, we should pick right because the origin satisfies this inequality. So as a result, we pick this one. Then we have non-negative to x1 and non-negative to x2. So as a result, my feasible region is given by this shaded area. Okay? Any questions? So, all right. So then I'm going to look at my distance maximization problem. I'm going to look at my isoprofit line. Okay. So let's start with the equation minus 3x1 plus 2x2 equals 0. So it goes through 0, 0. I need one more point. So for example, if x1 is equal to 2, x2 is equal to 3, right? So if x1 is equal to 2, and 2 is somewhere over here, then x2 will be equal to 3, and 3 is somewhere, well, down here, basically. Okay? So it goes through these 2 points. Sorry. If x1 is equal to 2, then x2 is equal to 3, so 3 is somewhere over here. Okay? So it goes through these 2 points right here. Something like that. Okay, so my lines are not straight, so they should be straight. Then I'm going to look at the improving direction. So it's given by minus 3 and 2, and minus 3 and 2 points in this direction, which is perpendicular. And if you keep moving this line, if you get the slopes right, basically, you're going to see that this is the optimal solution. So if you just draw these lines properly, okay, you're going to see that that's the best point you can have. And what I'm going to do is I'm going to try to solve this problem using the simplex method. Okay, so we know the graphical solution. Okay, so the question is, how can we solve this problem using the simplex method? So remember, we discussed the correspondence between basic feasible solutions and corner points. Okay. So as a result, since in general we cannot draw the geometry, we cannot see what the feasible region looks like, we're only going to work with basic feasible solutions. Okay, because we know that there's a one-to-one correspondence. And to do that, we're going to first of all take our problem and convert it into standard form. Okay. So we're going to convert into standard form. And we will also define a so-called dummy variable, which I'm going to call z, to represent the objective function. So dummy variable basically means there's something that does not really have a role in some sense, okay? And here's what I'm going to do. I'm going to rewrite my problem as follows. So I'm going to maximize, instead of writing the objective function directly, I'm going to maximize z, which is equal to minus 3x1 plus 2x2. Okay? So I'm just defining z as my objective function. And then I have minus 3x1 plus 3x2. I'm going to convert it into equality form, right? So I need a stack variable. So I'm going to use x3, and the right-hand side value is 6. Then I'm going to have minus 4x1 plus 2x2. Then I'm going to add x4 as my second stack variable, and the right-hand side value is 2. If you like, so let me just get rid of this for now, so that you don't get confused. So, so I will rewrite the objective function as z equals minus 3x1 plus 2x2. So z essentially will be a variable that represents the current value of my objective function. Okay? Now, what is my A matrix in this case? So if I look at this example, I have minus 3, 3, 1, and 0 as the first row. And the second row is given by minus 4, 2, 0, and 1. And my little b is given by 6 and 2. Okay? So then what I'm going to do is I'm going to sort of put everything on the left-hand side in this new equation. So as a result, I have z plus 3x1 minus 2x2 is equal to 0, right? So that's the same equation. Okay? And so we're going to set up the following tableau. I'm going to write down all variables, including z, x1, x2, x3, and x4, and then I'm going to add the right-hand side. And then I'm going to start with this equation first. So I'm going to just write down the coefficients. So 1, 3, minus 2, 0, 0, and the right-hand side is 0. Then I'm going to write down the first constraint. The first constraint does not involve any z, so as a result, it's going to be 0. The coefficient will be 0. Then I'm going to have minus 3, 3, 1, 0, and the right-hand side is 6. Then the second constraint does not again involve z, so I have minus 4, 2, 0, 1, and the right-hand side is 2. So the last two correspond to the constraints, and the first one corresponds to the objective function, basically, okay? So now we can think of this as I have 3 equations, and I have 1, 2, 3, 4, including z. I have 5 unknowns, basically, okay? Any questions? So let's take a break, and we'll continue after the break, okay?